Good afternoon, everyone. For today, we will present our review on a study titled Structural Properties of Gallium Nitride Films Grown on Sapphire by Molecular Beam Epitaxy. So as an introduction, so yeah, I will first discuss the motivation of the researchers for such study. So let's describe first the group 3,5 nitrides. So in this study, gallium nitride thin films, a member of group 3,5 nitrides epitaxially grown on sapphire substrate were characterized using X-ray diffraction and electron microscopy methods such as TEM. So studies of this group of semiconductor was halted before due to uh, some reasons. But now it has been recently gaining much attention due to their applications in optoelectronic devices such as light emitting diode, laser diode, both of which operate in the visible to ultraviolet region. So, and also uh, used in ultraviolet detectors. So however, the reason for their slow development is because it is difficult to grow films of high quality due to high N-type background and an inability to achieve P-type doping. So which is this characteristic are attributed from the high lattice mismatch with the sapphire substrate, resulting in high defect of surface film. So in fact, sapphire and gallium nitride are incommensurate type of epitaxy. So that is, there is no direct correlation between the lattice of the substrate and the thin film. Fortunately, it is again recently gaining attention due to rapid development of crystal deposition techniques, which made it possible to achieve films of high quality. So among these methods are hydride vapor phase epitaxy, metal organic chemical vapor deposition, and molecular beam epitaxy, which the latter was the one employed in the current study. So another problem arises. So since there is not enough evidence that correlates the microstructure of gallium nitride films with its physical properties, high-resolution synchrotron X-ray and TEM, so transmission electron microscopy, were employed to determine the correlation of the in-plane and out-of-plane structural order of the optical and electrical properties of materials, which could help in establishing proper figures of merit that will characterize the quality of the films. So in this study, there are different techniques and instrumentation involved from the fabrication of the film to its characterization. So molecular beam epitaxy, high resolution synchrotron, X-ray diffraction, and electron microscopy. So each of these will be discussed as we go along the presentation. So this experimental procedure in the study includes two types of sample with nominal properties as stated in the table below. So for the sample 1, it has a nominal broad out of plane X-ray rocking curve, while the sample 2 has a extremely narrow half width corresponding to its X-ray rocking curve. So the gallium nitride films are undoped and grown by molecular beam epitaxy on the C plane of sapphire substrate with aluminum nitride as the buffer layer. So sample 1 is evidently, as we can see in the values here, uh, thicker than the sample 2. So the buffer layer for sample 1 is 2000 angstrom with gallium nitride thin film of 6 microns. So while the sample 2 has 200 angstrom buffer layer and 0.36 micron gallium nitride buffer layer. So as I have mentioned, they are both grown by molecular beam epitaxy. However, sample 2 is grown at a slower growth rate relatively to the sample 1. So to describe this technique, crystal deposition technique. So molecular beam epitaxy was employed to epitaxially grown the thin film on the sapphire substrate. So sapphire substrate is considered the best choice because of its low cost, good quality, and availability in large size wafer. So here we describe the basic process of molecular beam epitaxy. So as we can see here, on the figure on the right is the schematic diagram of such technique. So it is a refined form of vacuum evaporation. It involves multiple molecular sources where the particles are deposited onto a heated substrate. So as we can see here in the schematic diagram, we have here the molecular sources, each of which contain the necessary molecular species in the gaseous form that will be deposited on the substrate. So each molecular source or molecular beam has a mechanical shutter which control the arrival rate of each species to control the quality or the desired type of thin film that will be deposited onto the substrate. So it takes place in a ultra high vacuum chamber to minimize the impurities. So it also uses collision-free molecular beams to supply the required species to the substrate. So here we can see additional ports in the MBE system. So these additional ports are placed to allow installment of measuring instrument for in situ and real-time measurements. So this what makes the molecular beam epitaxy advantageous, since we can perform in situ and um, real-time measurements. So such as electron diffraction. So for example, reflection, high energy electron diffraction, read, and Auger electron spectroscopy. So we can also perform mass spectroscopy while allowing the film grow onto the substrate. So therefore, with this information, we can see that the process is highly controllable at the atomic level. So moving on, for the actual XRD measurements, a diffractometer is used. So as we can see here in the schematic diagrams on the right. So generally, it has the following uh, components. So first is the X-ray source. Next is the incident optical system, which was not shown in the figure, but it is placed in between the sample and the X-ray tube. So the goniometer, which where the samples, the detectors, and all the system are placed to allow for the proper orientation. Then we have here the receiving optical system, and then finally the detection system. So we will describe each of this as we go along. So in this study, for the X-ray source, X-ray diffraction measurement were conducted at the X7A beam line of the National Synchrotron Light Source. However, it was officially shut down last September 30, 2014. But it was replaced with a more advanced and powerful ones, the NSLS2 version 2. So here we can see the schematic diagram of the old synchrotron um, facility. So here the X7 beam. So ito sila nag-perform ng experiment. And so why did they use synchrotron radiation? What are the advantages? So to obtain high resolution diffraction profile, since synchrotron radiation employs a high flux of X-ray beam, resulting in a higher resolving power and sensitivity for X-ray measurements. So as we all know, synchrotron radiation is still a continuous spectrum. So we need to use a monochromator from the incident optical system. So for the thin film XRD measurements, so most of the times the diffraction peak for the film and the substrate appear close together. Therefore, instrument should be of high resolution to be able to resolve the two peaks. Also, X-ray beam coming from the synchrotron source, as I have mentioned previously, is a continuous spectrum. Hence, monochromator was used to select the desired wavelength of 1.2104 angstrom. So in this study, a channel cut double crystal silicon 111 monochromator was employed to obtain a narrow beam of incident X-ray. So this is the schematic diagram for our monochromator. So for instance, we know that the X-ray beam is a continuous spectrum which contains a range of wavelength that could interfere the measurement. So after passing through this monochromating crystal, the exiting beam is highly parallel and monochromatic. So to explain why it is called a double crystal, a channel cut double crystal, this setup is contained in a single crystal. This another reflection made by the second crystal. So that's why it is a double crystal monochromator system. So the incident beam now will irradiate the sample placed in a goniometer. So typically, a four-circle goniometer is used to allow different sample, incident diffracted beam, and detector configuration. So as we can see here in the figure. So the circle corresponds to the axis at which goniometer can be rotated. So the following are the omega for sample rotation, then the phi for in-plane rotation, and then the chi for tilting axis, and the 2 theta for scanning detector. After passing through the sample, the diffracted beam is further enhanced by the another monochromator, but this time it is from the receiving optical system. So before it reached the detector. So in this study, germanium 220 analyzer crystal was employed. So similar to the incident beam monochromator, it was employed uh, to increase the resolution of the diffracted beam. So it also eliminates fluorescence emission, reduces background emission, eliminates specimen displacement and eccentricity error. It can also act as a slit, that is a very narrow angular slit, which provides a much higher angular resolution. So after this receiving monochromating crystal, finally the diffracted beam will reach the detection system, where it is qualitatively or quantitatively analyzed by the detector. So in this study, sodium iodide scintillator detector was employed. So due to its high detection sensitivity, low noise level, and easiness of handling. So moving on, for our results, for the first part of the results, we can see here the XRD profiles of the sample 1 and sample 2. So the synchrotron X-ray diffraction profiles for the 002 Bragg peaks. So 002, that means it corresponds to the out of plane measurement. So the wavelength is 1.2104 and the scan method is theta 2 theta scan. So as we can see here, sample 1 has a narrower peak than that of sample 2. So visually, makita naman natin. So the dots here represent the experimental data. So naka-plot. And then the solid lines are the least square fits using pseudo-void function. So sample 1 employs a single fit, as we can see here, while the sample 2 employs a two-peak fit due to the presence of broad shoulder. As we can see here in the peak of sample 2, excuse me, we have a shouldering. So we can imagine it as a two peaks superimposed within each other. So this is the first peak, the broader one, and the narrower peak. So the two peak fit method was employed to determine the peak width of the sample 2. So the values were extracted from these profiles and uh, placed in this table. So least squares peak fitting results. So for the Q scan, it will provide the full width at half maximum, which corresponds to the coherence length of the thin film. That is, it can be viewed as the crystallite size since we use the Scher's formula to estimate its value. So for sample 1, we can see that it has a narrower peak width than that of sample 2, 0.094 degrees versus 0.0285 degrees, while the coherence of sample 1 is much greater than that of sample 2 with 21,000 angstrom and 3,200 angstrom from for sample 2. So what are these values signify? So the importance of these values are, so the coherence length is related to the quality of the film since it determines the degree of lattice coherence. So it also describes the amount of submicron defects such as dislocations and crystallographic order. So since the calculated coherence length of sample 1 is on the micrometer level, that is same order with the film thickness, it can be concluded that the sample 1 has a better film quality than the sample 2 in terms of its out of plane measurement. So the following, the next results will be presented by the next presenters. So that's it for the first part.